What if you could put your .NET application and everything it needs in a box, including all its files, dependencies, configuration settings, and any bootstrapping scripts? What if you could also include the .NET runtime and even the operating system required to run your app? Then we could take that box and place it as is in your production server and have it run your app exactly as it was running in your developer machine. Not only that, what if we could place as many copies of this box as your server allows and have them all start your app really fast in seconds, not minutes? Well, that box exists today, and we call it a container, a lightweight, isolated environment that includes everything needed to run your app. And the most popular software to run containers is Docker, a platform for packaging and running container-based applications that ensures your app works the same way anywhere, eliminating the "it works on my machine" problem and allowing you to deliver software fast and consistently across environments. In this course, we will start by understanding why you should use Docker containers and what kind of problem they solve. Then, we will explore the difference between containers and virtual machines and why containers are so popular these days. Next, we will get started with Docker by going through the different components of the popular Docker desktop application in our dev box. Then, we will understand the relationship between containers and container images, followed by a series of practical exercises where we will use the most popular Docker commands by downloading and running a popular public Docker image. After this, it will be time to create our own Docker image for a simple .NET application. And we will learn how to do this both via traditional Docker files and also via the newer container support in the .NET SDK. Here we will also explore how to version our images so that we can package and distribute updates to our application. And then we will learn how to publish our own images into the cloud and how to run them beyond our dev box. To close, I'll give you the big picture of how containers fit in the modern DevOps lifecycle. So let's start by understanding why Docker containers are a big deal and what problem they solve. Let's start by going back several years to the time before virtualization. Here we have a software developer who has just completed a feature or bug fix that needs to be deployed to the production server. The operations team will coordinate this deployment to ensure minimal downtime. As usual, our developer sends the binaries and any other related files to the ops team. Ideally, the developer also will provide a series of deployment instructions that will guide the ops team and reduce the chance of errors. The operations team follows the instructions and deploys the new binaries to the production server. But unfortunately, things don't go as expected and the updated application crashes a few moments after completing the deployment. What could have gone wrong? Well, to start with, we may want to check that the server has the correct version of the .NET runtime that the developer specified. Then, we may also want to make sure that the server uses the closest OS version to the one used by the developer in his box. Next, we could also check if we missed any required files or configuration settings. Perhaps ops missed a deployment step, or the developer left a step out of instructions. If we look at the server resources, we may discover that there's not enough RAM or CPU because the other apps we are running there are already using a good chunk of them. Another possibility is a conflict between our new binaries and the many DLLs that have already been placed in this server by other apps. And of course, it could all be due to missing permissions since the server environment is heavily restricted as compared to the developer box. After asking the developer for advice, he assures us that it all works on his machine, so the issue is probably not on his side. These type of deployments are now known as bare metal deployments, since you deploy directly to the physical host. At a high level, the software stack would look like this. At the bottom, you have the hardware components, like RAM, CPU, and disk. Then you have a specific version of the operating system, followed by a version of the .NET runtime. Finally, you will deploy one or more applications that have been tested in this specific combination of OS and .NET runtime. Because the applications were deployed directly to the bare metal, these deployments suffered not only of all the issues we just saw, but also several other issues like hard-coded paths, finding that required ports are already in use, not having enough servers to scale the apps, wasting the hardware resources of the few servers available, very slow provisioning that will require hours or days to complete a deployment, and when needed, how to roll back to a healthy previous deployment. Virtualization in the form of virtual machines came to address many of these bare metal deployment issues. Let's see how it works. We start again with the physical hardware, like your CPU, RAM, and disk. But above it, there is a special piece of software called the hypervisor. You can think of the hypervisor as a resource manager. It takes your physical hardware and creates virtual versions of these resources, allowing multiple virtual machines to safely share the same physical computer. A virtual machine, or VM, is exactly what it sounds like, a computer that exists as software rather than physical hardware. Each virtual machine has its own operating system, its own version of the .NET runtime, and a version of our application. You could also create an image that can work as a template for your VM, so you can provision multiple exact copies with minimal manual work. You could keep going, spinning up as many VMs as possible in this server for each of your applications, each one completely isolated from the other, which would even allow you to use a different OS or OS version on each one without impacting the others. This type of virtualization enabled several important benefits: perfect OS and runtime version matching for each application, a clean, isolated environment for each deployment, better control over resource allocation for each VM, pre-configured permissions in the VM images, predictable paths since each VM is identical, easier scaling of your apps by just adding more VMs, faster provisioning compared to bare metal, and simpler rollbacks using VM snapshots. However, virtualization also introduced its own set of challenges. There was a significant overhead in terms of RAM and disk space, since each VM included a complete OS. Creating VM images was an hours-long process, very painful when errors were found on an image. Even though faster than bare metal, VM provisioning still took several minutes. VMs had slow boot times since they had to boot an entire OS. You could only run so many VMs per physical server, depending on each VM's requirements. Many times, you ended up with tons of wasted resources, again due to having an entire OS on each VM. Managing multiple OS instances also meant you had multiple systems to patch. And it was quite challenging to version control the VM images. These challenges would later lead to a different kind of virtualization. Containers represent the next evolution in virtualization technology. Let's see how they work. We still start with our physical hardware at the bottom, but instead of a hypervisor, we bring back the operating system. Now, the OS is divided into two main components, or layers. The kernel, which is the core part of the operating system that directly controls the hardware. It handles memory, schedules, processes, talks to devices, and enforces security. And the user space, which is where your applications and most system services live. Programs here can't directly touch hardware and must ask the kernel whenever they need something. This separation keeps your system stable and secure. Also, it allows you to take advantage of one of many OS distributions, like Ubuntu, in your user space, while letting the Linux kernel manage the system resources. Now, instead of virtualizing the entire operating system like we did with VMs, we add something called a container runtime. Docker is the most popular container runtime, and it sits between the operating system and our applications. Its job is similar to what a hypervisor does for VMs, but much more lightweight. Instead of creating entire virtual computers, it creates isolated spaces within the existing operating system, which we call containers, where the applications can run. What exactly goes inside this container? First, we start with just the operating system user space components, Ubuntu's user space in this case. Notice we are not including a full OS, just the user space components. Next comes our runtime environment. in this case, the .NET runtime that our application requires to execute. And finally, at the top, we add our application itself. This layered approach is fundamental to how containers work. Instead of having a complete operating system like in VMs, we only include the specific components our application needs to run. Everything else, particularly the kernel, is shared with the host operating system. Now let's add a second container. This one will run a different application, and interestingly, it can use a different Linux distribution user space, CentOS in this case. Here's what makes containers so powerful. Even though these containers use different Linux distributions in their user space, they can still run side by side because they both share the same Linux kernel underneath. We can easily spin up more instances of our applications by creating more containers. Each container remains completely isolated with its own user space, runtime, and application, yet they all share that same Linux kernel at the bottom, which makes scaling both simple and efficient. So this new virtualization approach helps us solve most of the challenges we had before with VMs. Containers share the OS kernel and only require user space components, dramatically reducing RAM and disk usage compared to full VMs. What takes hours with VMs takes seconds with containers, since you're just creating a lightweight manifest rather than copying entire OS images. Containers start as fast as regular processes since they don't need to boot an OS. They are just namespace processes that use the running host kernel. Containers package everything needed to run the application in a standardized way, eliminating "it works on my machine" problems. You can run far more containers per server than VMs since there's no OS overhead for each instance. Containers share the host OS kernel and binaries, eliminating wasted duplicate resources that VMs require. Container images are immutable and use layered file systems with built-in versioning, making them far easier to track and control than VM images. Now, this might make you wonder, why would we ever use VMs if containers are so efficient? And the answer is that instead of choosing, you can combine both technologies to get the best of both worlds. Here we have our hardware layer followed by our hypervisor on top, which lets us create those fully isolated virtual machines we talked about earlier. Inside each VM, we've got a complete operating system with its own kernel. VM number 1 here is running Linux, while VM number 2 is running Windows. Now, inside each VM, we can run a container runtime like Docker, which lets us host multiple containers that share that VM's kernel. This hybrid approach is exactly what major cloud providers use to run thousands of customer workloads. It gives you the bulletproof isolation of VMs between different customers or environments, while still letting you get all the efficiency and speed benefits of containers within each VM. To run Docker containers in your Windows or Mac developer box, you install Docker Desktop, which is a developer-friendly application that bundles all the necessary components to run Docker. Let's see how it works at a high level in a Windows machine, since that's the one that we'll be using across this course. At the very foundation, we have version 2 of the Windows Subsystem for Linux, or WSL2. This is Microsoft's compatibility layer that lets you run a Linux kernel directly on Windows. WSL2 creates and manages the utility VM, which is a lightweight virtual machine used to provide a seamless Linux environment for your containers. WSL2 runs a Linux kernel inside this VM, which, as you know, manages the hardware and provides essential services. Now, within this utility VM, we have a special Linux distribution called Docker Desktop, which is managed by Docker Desktop and provides the user space environment necessary for running the Docker engine and your containers. Here, we will find the Docker daemon, also known as Dockerd. This is the core process of Docker, which manages all your containers, images, networks, and volumes. It listens for commands and executes them. Here is also where you are going to find your containers, the isolated environments where your applications run. They share the Linux kernel, but have their own separate file systems and processes. Now, how do we control all of this? That's where the Docker API comes in. The Docker daemon exposes this RESTful API, which acts as the interface that provides the set of commands and protocols that let you tell the daemon what to do. And one way to interact with that API is through the Docker command line interface, or CLI. When you type commands like docker run or docker build in your terminal, you're using the CLI, which then translates these commands into API calls that the Docker daemon will receive and understand. But there's also another way, the Docker GUI. This is a user-friendly graphical user interface provided by Docker Desktop to interact with the Docker Engine components. It talks to the Docker API in a similar way as the Docker CLI, sending commands and giving you visual feedback. We also just mentioned the Docker Engine. This term refers to the core components that make Docker work. So it is composed of the Docker daemon, the Docker API, and the Docker CLI. It's the combination of these elements that allows you to build, run, and manage containers. In essence, Docker Desktop orchestrates all these components, providing a seamless and efficient way to run Docker containers on your developer box. Now let's see how to get started with Docker by downloading and running Docker Desktop in our dev box. To get started with Docker, you can go ahead and open up the docs.docker.com page, which is the main page for Docker documentation. And from there, you can either click on the Get Started link over there or on the Get Docker button over here. So let's go ahead and use the button. So let's click on Get Docker. And this is going to take you to this page where if you scroll down a little bit, you're going to find options to install Docker either for Mac, for Windows, or for Linux. So it really depends on the OS that you're going to be using with Docker. In my case, I'll be using Docker Desktop for Windows. I have a Windows 11 box here, so I'm going to click on Docker Desktop for Windows, and this will take you into the page where you're actually going to find the buttons to download the installer, as you can see here. Now, it will depend. I mean, even on Windows, you can either have an x86 or x64 system or even an ARM system. So just go ahead and pick the one that makes most sense for you. Now, I'm not going to go ahead and download and install it because I already have it installed in my box, but one thing to notice is that when you go through the installation, you're going to have the option to either choose the WSL2 backend for x86 or x64 or the Hyper-V backend, right? Now, which option to choose? You're going to see that by default, it's going to offer you WSL2 backend. And for most cases, that's really what you want to use because WSL2 is going to be much more resource efficient, it's going to be faster, and it really integrates much better both with Windows and with the Linux kernel. So just go ahead and choose WSL2 backend, but just know that there's also this Hyper-V backend option if you want to use that. Now, after you install Docker, you will have to go ahead and start it. And to start Docker, all you have to do is open up your start menu, at least on Windows, and then just type Docker, and you're going to find Docker Desktop is going to be your main option over there. So I'm going to click on Docker Desktop. And what this is going to do is start both the Docker engine and also open up the Docker Desktop GUI, as you can see right here. Now, this is the main graphical user interface that you can use to manage all of your Docker artifacts. For instance, here where you can see all of your containers, right? So this is the containers option, but you can also go into images, right? So this is where you're going to see all of the images that you have downloaded into your machine. And you can also see any volumes that you have created that support your container. We're going to be talking more about volumes later on, but just know that this is the main section where you can manage all of this. Now, one thing to point out is that you also have this gear here where you can configure a few settings for your Docker installation, right? So if you click on that one, you're going to be taken to this screen, and this is the place where you can do a few adjustments if you need to, right? So for instance, if you want to start Docker Desktop automatically whenever you sign into your computer, well, here's the option to do that, right? So Docker Desktop is not going to be starting automatically just because you start your machine. You have to either start it manually, as you just did, or by ticking this option here. Just keep in mind that starting Docker Desktop does not mean that your containers start. You do have to start those containers manually. Now, another option to take a look here, and actually let me scroll down a little bit here. So you can also notice that here we have enabled the WSL2 based engine, which as you can see, is it has better performance than the Hyper-V backend, right? So it is much better to use preferred WSL2. Now, another thing is in this resources section over here, if you click on resources, what you're going to see if we scroll up a little bit is that here we have an option to select where is that we want to store this image location for WSL2. Remember that we said that there is a utility VM that WSL2 is going to be using? Well, that VM is going to grow over time as you start having more and more Docker images in your box. So if you want to, you may want to change the location here to a location where you have more space available, right? I already did make that change. I switched to my D drive where I have more space. And you can do the same. Just be aware that changing this path is a little bit challenging. That's what I found as I try to do this because of some permissions. But just so you know, this is the place where you can make those changes. Let me close this settings screen. And one thing that we may want to do at this point is to, well, make sure that Docker is actually running, right? And one way to tell this is by taking a quick look at the engine running message. Let me show you that over here. If we go all the way down here, there is this engine running message over there. That means that Docker is running in your machine. But that's one way to do it. Another way, if I taking a look at your status bar over here, if we look here, here is the Docker well. So if you see that icon over there, it means usually that Docker is running happily in your machine. But of course, you don't have to use a GUI to tell that Docker is running. Another way is to use the Docker command line interface or CLI. So let's take a quick look at that CLI briefly now. So to get there, you can just open your favorite terminal application. Like in Windows, I'm just going to be using the Windows terminal. So I'll open that. I'll maximize this. And here you can do a couple of things. So in this case, I'm going to go ahead and just say Docker version, right? By doing that, you're going to confirm what is the version both of the client and server parts of Docker Desktop. Right, so you can see here, here's the version of our Docker client, and here's the version of the Docker engine. And since we are able to see both of them, it kind of means that Docker is working properly. Otherwise, you will have seen some sort of error on this screen here. Let me clean this. But another way to tell that Docker is really working for you is by actually running very quickly a very simple Docker image. And to do that, what you can do is just type Docker run. Let's go for hello world. Okay, so hit enter. What this is going to do is go ahead and find the hello world Docker image from a place called Docker Hub, which we're going to be talking about later on. It's a public place where we're going to find thousands of Docker images, including this hello world image. And as you can see, it was not able to find the image initially, right? It was not able to find it. So it went ahead and downloaded it from Docker Hub, right? And then it executed that image as a container in your box, right? And you can see here, hello from Docker, over here. This message shows that the installation appears to be working correctly. So this is a nice image to verify that the installation is correct. And you can see here in these 4 steps, it tells you what it did, right? So the first thing is that your Docker client, the CLI, connected to the Docker daemon, as you can see there. And then the Docker daemon pulled the hello world image from Docker Hub. And after downloading that image into your box, the Docker daemon created a new container for that image, which runs the executable that produces the output that you're seeing right now. And that output was sent finally from Docker daemon back into your terminal, right? So very nice image, and it actually tells you that Docker is running properly in your box. However, we just started talking about this concept of images and containers, right? You may be wondering, well, what is an image? What is a container? What is the difference between them? So let's go back into slides for a moment so that we can talk about Docker images and containers. To understand what a Docker image is, think about the steps you would normally perform to prepare a machine to run your .NET application. Assuming all you have is some sort of hardware, you would start by installing an operating system. Then, you would install the version of the .NET runtime required by your application. Next, you would likely copy all of the application files and install or restore all of its dependencies. Then you may also need to configure the environment or a few settings which may affect the way that your application executes. And finally, you would run your app. The end result after executing each of these steps is what we call a Docker image. It is a blueprint or template that contains everything needed to run your application. Also, each step, when performed to create a Docker image, is known as a layer, with each layer representing a specific instruction to create your containerized app. Now, the whole point of building a Docker image is to share it in a place where other devices can access it. This place is known as a container registry, and you can think of it as a repository for Docker images, similar to how GitHub stores your code. Any device that has access to the container registry and that is running the Docker engine can now download the Docker image. But what about the Docker containers? Well, a container is a running instance of an image, an isolated environment with its own file system, networking, and processes, all based on the instructions in the image. Inside each container, your application runs in isolation with its own resources and its own view of the operating system, but sharing the same kernel as the host. Now that we understand the difference between Docker images and containers, let's see how to work with Docker images and containers in practice. The best way to solidify our understanding of Docker images and containers is by working with an existing image via several commands exposed by the Docker CLI. Now, where do we get one existing image? Well, that is exactly the purpose of Docker Hub. So Docker Hub, which is located at this page over here, hub.docker.com, this is the biggest repository of publicly available Docker images in the internet. And here you're going to find Docker images for any software that you can think of, right? So if you start scrolling down here, you're going to see that there are many images for many popular software, as you can see here. And in fact, they are categorized, as you can see on the left side. There are categories for many of these images. You're going to find thousands of images in here. And some of the best images that you can use here is these ones that are classified as Docker official image. Now, if you click here, what you're going to go is into a filter of a bunch of Docker images that are pre-built and they are trusted and maintained by Docker itself, right? So they follow strict guidelines for quality, security, and consistency. So they're essentially a reliable foundation for your projects. And here you're going to see many popular pieces of software like Memcached, here's Nginx, here we have Alpine, Ubuntu, here's Redis, Postgres. So if you want to use any of these pieces of software for your project, all you have to do is pull down that image into your box. They are all free and just start running them. So this is exactly what we're going to do now so we can get a much better experience with how Docker images and containers work. What we're going to do is actually use the Nginx image, this one over here. Let's go ahead and click on that one. And in this page, you're going to get all of the details about the Nginx Docker official image, as you can see here. But the main thing that I want to call out in this page is the instruction that you can use to start, well, downloading or pulling that image into your box. And you can see that right here on the right side, Docker pull Nginx. So Docker pull is the command that you can use to download the image into your box. So what we're going to do is just click on this copy button over here. So let's click on copy. And now let's go back into our terminal right here. And to pull down that image, all you have to do is just paste the command and hit enter. Now what's going to happen is that all of the layers that compose the Nginx Docker image are downloaded one by one or perhaps in parallel into your box. The idea of each of these layers is that each layer represents some sort of command executed when creating an image. So for instance, you can think about this first layer over here could be the minimal Debian or Alpine Linux based image for Nginx. And then this second layer over here could be the layer where we add the Nginx package and all of its dependencies into the image. Then perhaps this one here is a configuration layer, right, to copy a bunch of Nginx configuration files. And maybe one of the last ones, perhaps this one over here, is the one that sets the command to go ahead and start Nginx. All right. So each layer is just keeping track of the changes into the Docker image. They are cached, and many containers can share the same underlying layers, which is going to save a lot of this space. Now you can see here that the image was downloaded for the Nginx latest tag. And in fact, we can now do the following. Let me just clean this. And what you can do now is type Docker images. You're going to see that at this point, we do have our Nginx image right here, right? It is right there sitting next to the Hello World image that we worked on a moment ago. Now you can see the images not just in the terminal, but also in the Docker Desktop GUI. So if we open up the Docker Desktop GUI over there, you're going to see that now we go to images, and we're going to find our Nginx image right here, right? With a tag, the image ID, which is a unique identifier for this image, when it was created, and the size on disk. Here you can also see that we not only have the Nginx image, but also the Hello World image. And you can tell by this green dot over here that the Hello World image is actually in use by a container that we created a bit earlier in the video, right? Container, here's the container that we created before, but the Nginx image is not currently in use. Now, one question that you may have is, well, where exactly is this image living in my box, right? So I didn't see any kind of file actually getting downloaded. And the thing is that remember that we said that we're using Docker Desktop in conjunction with WSL2, the Windows subsystem for Linux. And that subsystem actually has a utility VM where it has the distro, where it has all of our containers and images. So these images are going to live, if you go into settings, remember that we said that here in resources, there's a location where we specify where is that we're going to be storing everything related to Docker Desktop. So in that location is where you're going to find the files that define the virtual machines or virtual hard disks where Docker Desktop is going to store everything about your images and your containers. I'm not going to go into that directory right now, but that is a place where those images are going to live, okay? Now, there is one important concept to understand here. As you can see here, it says tag, right? It says tag. And this is a very important concept to understand regarding Docker and regarding how we're going to be doing versioning for our images. So let's get back into our slides for a moment so we understand better this concept of Docker tags. Let's understand the concept of Docker tags by going through a real-world example. Let's say we just finished the first version of our application and we turn it into a Docker image to prepare it for deployment. Since this is our initial release, we will assign it a tag, 1.0 in this case. This isn't just a random number, it's a reference point or our way of saying that this is the first production-ready version of our application. Then, life happens. We discover a security vulnerability, we patch the application, and generate a new Docker image. Once again, we tag it, but this time with version 1.1, so we can easily distinguish it from our first version. Sometime later, some performance issues show up, so we fix those, generate a new image, and we tag it with 1.2. When a critical bug appears, we fix it and tag the new image with 1.3. And because why not, one day we decide to fully rewrite our API, which also brings breaking changes, so we tag the new image with 2.0. Now, here's where it gets interesting. We can have more than one tag for each of these image revisions. For instance, version 1.3, which has proven reliable, can also get the stable tag, while our newest version, 2.0, automatically gets the latest tag. Why would we do that? Well, a developer that needs the most reliable version of our app before breaking changes can pull the stable tag, while another developer who needs to use the latest API can just go for latest. So as you can see, this tagging system is a great way to maintain multiple versions of your application simultaneously, giving your team the flexibility to choose between stability and cutting-edge features while keeping a clear history of every change. Let's see now how to use Docker tags in practice. As you may have noticed, so far we've been using the latest tag of the images we've been working with, right? And you can confirm that over here where we have the latest for both Nginx and Hello World. But that is not the only tag or the only version available on any of these images. In fact, if we go back into Docker Hub over here, here's the page for Nginx and Docker Hub, we're going to notice that there are actually many tags available for our Nginx image, right? Most of them are going to start with one of the versions, right? 127.4 is the latest that we can see here. And in fact, if we do a Control F here to look for latest, what we're going to see is that the latest tag actually corresponds to 1.27.4, but there are many other tags for many other versions of this Nginx image, as you can see. So it's really up to you to choose which tag to use. Now let's say that we wanted to use a different version. For instance, the most stable version of Nginx as opposed to the latest bleeding edge version. What you can do here is just look for, let's say, stable. And here you're going to see the one that actually shows as a stable, which is going to be in this case version 1.26.3. So let's see if we can pull down 1.26.3. Let's go back to the terminal and let's do the following. Let's clear this and let's do docker pull nginx. And what you can do is just add colon here and then you put the specific tag that you want for that image. So we said 1.26.3. So I'll hit enter. What's going to happen is that once again, the layers that we are missing are going to be downloaded. This is not all of the layers, but only the layers that represent the changes between the previous image of Nginx that we had and the one that we're pulling down now. So if we now do Docker images, we have both version 1.26.3 and also the latest version. But another interesting thing here is that, well, we saw in the page here that this is also tagged as a stable. So what we can do also is just say docker pull nginx stable. Now, the cool thing here, as you notice, is that nothing really was pulled down, nothing was downloaded. And that is because we already have the layer that corresponds to that tag, to stable tag. So if we now do Docker images, we're going to see that both Nginx 1.26.3 and stable actually have the exact same image ID, because those two are both pointers to the exact same image, right? And so that's the key thing about these tags. You can use multiple tags to define different points in the life of your images. And that's the key way that you can track the versions of these images. You can always go into the version that makes most sense for your application. Now that we understand this concept of tags and how to download images, well, let's go ahead and actually run an image so that we can turn it into a container. So let me clear this. And to run an image, all you do is do docker run. Just like we did hello world, we can do this time nginx. So that's going to go ahead and take that image and turn it into a container, which, as we said, is a self-contained process with its own environment that executes the application that has been packaged into our image, right? And what you can see here is really all of the logs that the application inside the container, in this case Nginx, is emitting into our terminal. And you can see, I mean, at this point, we are in what we know as an interactive session, so we cannot really do much in this terminal here because of the way that we execute the image, but we can take a quick look at the Docker Desktop GUI, where we're going to see in the Containers tab. So if we go into Containers on the left hand, over here, we are going to see our running Nginx images right here. And this is the random name that was assigned to our container with its corresponding container ID. Okay, now to stop this container, you can either click on the stop button over here, you can click on that, or back in the terminal, we can just do, at least on Windows, Control-C, and that's going to stop the process, right? And if we go back here, you can see that the image is no longer running, right? So it's now stopped. Now, if we go back into the terminal and we clear this, one command that you can use to take a look at all of the running containers is Docker PS. This is a way to show all of the running containers. But right now, we don't really have any running containers, so we are not seeing anything. So if you ever want to see all of the containers that may be, for instance, stopped as they are right now, you can do Docker PS -- all. And that is going to show all of the containers that have already stopped. So we can see our Nginx and our Hello World containers right here in a stopped state. Now, one thing to understand is that every time that we execute a Docker run, so if I do Docker run once again, Docker run Nginx, this is actually creating a brand new container that has nothing to do with the container that we started a moment ago, and that is actually stopped. Now we have this other container up and running. And if I do Control-C and I do Docker PS -- all, we're going to see that we have two Nginx containers running over here. I mean, stopped in stop state right here. Each of them with their own random name. So just by stopping our interactive session with the container doesn't mean that the container goes away. It's just going into stop state. Now, as you saw, it is a bit troublesome to start these containers, and we don't have a good way to interact with it because it just takes over the interactive session in our terminal. That's kind of one issue. And another issue is all of these strange random names that are getting assigned to our containers, which are going to make it a bit challenging to work with the containers. So what we can do to address both of those is use a few more parameters in our Docker run call so that we can run in kind of a detached mode with these containers and also assign some name to them. So let's do this. Let's clean and let's do Docker run. But this time we're going to assign the -d parameter here, the -d argument. That means detach. It means do not do an interactive session, just run the container in the background. Okay, so that's one thing. And the other thing is the name parameter, which is going to assign a specific name to our container. So let's say we're going to call this one nginx test. And the last argument is going to be the actual Docker image. In this case, it's going to be nginx. Notice that if I don't say :latest, by default, it is going to go for the latest tag, right? Otherwise, you have to specify any other tag that you want to use. But let's just keep going with the latest. So I'm going to just do nginx, hit enter. And as you can see, this time we don't see an interactive session here. It just gives us an ID related to that container. The container is running, but we don't have an interactive session. Now, if I go ahead and clean this and do Docker PS, we are going to see that our container is up and running. And you can see the container ID right here, the related image, how much time ago it was created and how much time it's been running, the name that we assigned to it, right? So this is nginx test, and also the port where the container is listening. Once again, you can always take a look at these containers by going into the Docker Desktop GUI. If you go to containers, you're going to see that our nginx test container is up and running here. You can notice that via the green dot here and also the stop button over there. Now, you can stop this running container either by clicking on stop, or if you come back here, since it is detached, what you can do is use the name that we assigned to the container to stop it. So you can say docker stop and then nginx test. Okay, so that stops the container. If we do docker ps again, we notice that the container is no longer running. But of course, eventually you may want to, well, rerun your nginx container. But the trick is that if we, let's clean this, and if we go ahead and try to rerun our nginx test container like this, I'll hit enter, you're going to get this error response, kind of a conflict. And as it says here, well, the container name nginx test is already in use by this container with that ID, all right? And that just takes us back to the fact that the containers, when they stop, they're still there, right? You cannot reuse the same name for a container that already exists, even if it's not running currently. So if you do docker ps --all, we're going to see that our nginx test container is right there, stopped, but right there. How do you deal with a container that is in this state? Well, you could restart the container if you wanted to, but that's not really usual. What you really want to do is just get rid of that container and restart a brand new container with the name that you want to assign. And to do that, all you have to do is docker rm and then the name of the container. So in this case, nginx test, and that will go ahead and actually destroy or remove that container completely. So this time, if we try to go ahead and rerun our container, it is going to run without any issues. Now, if you ever want to go from a container that is currently running into getting it completely removed without having to stop it in the middle, you can do a force removal. So for that, what you can do is docker rm nginx test. And you can, for instance, if you just do it this way, that's not going to work because, well, the container is running. But if you do docker rm nginx test -- force, that will actually go ahead and force the removal of that container even if it is running. However, there's actually a better way to do this, right? If you know that you only want to use this container as an ephemeral container, you want to use it once and then just destroy it to create one the next time, what you can do is the following. So you can do docker run, and we'll use all of these parameters as we did before, but we're going to add one more argument that is going to be --rm. --rm means that as soon as we request stopping a container, it has to get removed, right? So I'll hit enter. And so if you do docker ps, we're going to see that the container is running. But now if I stop the container with docker stop nginx test, it's going to not just stop it, but completely remove it. And we can confirm that by doing docker ps --all, we're going to see that there is no nginx test container running anymore. It is completely gone. And we can also see that in our Docker desktop GUI. Let's perhaps click on images, containers, and we're going to see that nginx test is completely gone. It's not here. And since we now know how to run our containers with a specific name, let's actually go ahead and get rid of all of these randomly named containers by just clicking over here. I'm going to click there, and I'm going to go ahead and just click on this red delete button over there, and that's going to get rid of all of those containers. The images are still there, as you can see, but the containers are now gone. Now, if we go back into our terminal, right? And let's clean this. And we rerun our Nginx test container, right? Like this. And let's also do Docker PS to get the details about this container. We're going to see that we have this thing called a port. It says port 80 here. So perhaps that would make you think that is the port that you can use to access our Nginx server that is running this container. That's something we can actually try out. So let's see what happens if we go into our browser over here. And what I'm going to do is just use this browser to go into localhost. In this case, it's going to be 80 because it reports port 80, right? So I'll hit enter. And what we're going to notice is that, well, that actually doesn't work. But what does that mean? Why is it that it reports that it is exposed in port 80, but we cannot access it? Well, that's because we need to understand how exactly port mapping works in Docker. So let's go back to the slides so we understand better this concept of port mapping. Let's understand port mapping in Docker. Here we have our host machine, and we are currently running an Nginx Docker container, which by default listens on port 80. Now we open our browser and try to send an HTTP request to our container. However, all we get is an error response. The reason why this is happening is that Docker containers are completely isolated by default. Even though Nginx is listening on port 80 inside the container, that port isn't accessible from our local host network. So when we try to access localhost 80 from our browser, the request never reaches our container. To fix this, we need to create something called a port mapping. We'll tell Docker to map a port on our host machine, let's say port 8080 to port 80 inside the container. Think of it as creating a bridge. Any traffic that arrives at port 8080 on our host will automatically be directed to port 80 in the container. It doesn't have to be port 8080, any available port will do, as long as it is mapped to the port where the container is listening. Now, the browser can send a request to localhost 8080, which, given our configured port mapping, will be forwarded by Docker to port 80 inside our container. Nginx receives the request, processes it, and sends back a successful response through our mapped ports ending in our browser. This is port mapping in action. It creates a tunnel between specific ports on our host machine and our container, allowing them to communicate while still maintaining the container's isolation. Now let's see how to use Docker port mapping in practice. Here we are back in our terminal, where a moment ago we noticed that the container is running in port 80. It says right here. But as we know by now, that is not going to be enough for us to reach the Nginx server inside this container because we have not introduced the proper port mapping. So let's see now how to create this mapping. Let's start by first stopping this running container. So I'm going to do docker stop Nginx test. Okay, let's clean this. And what we're going to do is to execute a very similar command, docker run, with the same arguments as before, but we're going to add one more argument, which is going to be for this port mapping. So we're just going to add here -p, and then we want to specify first what is going to be the port in our local host network that we want to use for this mapping. So in this case, let's say we go for 8080, and then as we know, the container is already listening on port 80. So as you can see, left side is going to be the port in our local host network, and right side is going to be the port where the container is listening. Now you don't have to use port 8080, but it has to be a port that is available or not in use in your local machine. Now let's go ahead and run this. So I'll hit enter. The container is running now. But notice that if I now do docker ps, we are going to see the mapping actually over here. It clearly says that in our local machine, here represented by 0000, we have port 8080 being mapped into port 80 on the container. And because of this mapping, we should be able to now actually reach our Nginx server. So let's go back to the browser. Remember that before we had just this page because we could not connect, but now we can go into 8080. And as you can see, we're immediately greeted with this welcome to Nginx page here, which is the default page of the Nginx web server. Now, like I said, it doesn't have to be port 8080. So if you come here and let's just do docker stop Nginx test, and then let's clean this and let's run the same docker run command again, but let's say we want to do port 7000 now, right? Could be any other port. Hit enter. Now we go back to the browser. Of course, if we try to refresh this, not going to work because we're not listening or mapping port 8080, but we are mapping port 7000 in this case, right? Same port in the container, but different port in our localhost network. Now, let's say that we want to make some sort of a change in this home page that we're seeing here. How can we do that if that is running inside a container? Well, that is something that we can actually do, because one thing that you need to realize is that a Docker container has what we know as a main process, right? In this case, it's the Nginx web server, but you can also spin up additional processes to do some sort of a task inside this running container. So that's going to spin up kind of a temporary session to do some work in the container. How to do that? Well, let's go back into our terminal here, and let's do the following. Clean this, and let's say that we want to start a bash session inside the running container. So what we're going to do is docker exec. So docker exec is the command that you can use for this. And in this case, we do want an interactive session. We're going to do IT for interactive session. Then let's add the name of a running container. So nginx test. And then the actual extra process that we want to run inside this container, which is going to be, in this case, bin bash. Now notice that our prompt has changed here, right? So this here is no longer a PowerShell prompt, it's actually a bash prompt, because we are now running in this, as it says here, as the root user inside our containers. We are kind of inside a small window that allows to enter this running container, and we can actually take a look at what's going on inside. So for instance, if I do, in this case, ls, I am able to list all of the directories that are inside our container, which, as you can see, these are more of a Linux file system as opposed to a Windows file system as I have in my machine. So how do we make changes to that home page of Nginx? Well, all we have to do is just to switch to the right directory. In this case, we want to go into usr. We can do ls here too. And then we can go into share. And then here we can go into Nginx. Okay, where we have only this HTML directory where we can actually go into, right? HTML. Okay, so if you do ls here, we're going to see that we have two files, right? So we have this 50x.html and index.html. So index.html, this is the file that actually contains that home page for Nginx. And we can totally go ahead and make changes to it. So what I'm going to do is add something not fancy at all. It's going to be just one line, but just to show you that you can actually make changes to what's going on inside the container. So what we're going to do is an echo command, and perhaps let's use an h1 so it looks big. And it's going to say just hello there. Right, let's close this. Let's hope we don't make any typos. Okay, and then let's pipe the output of that into our index.html page. Okay, this should have the effect of replacing everything in that HTML file with what we just defined there. So I'll hit enter. And now we can go ahead and go back to our browser over here. Let's see what happens if we refresh this. I'm going to refresh and notice that the text of this HTML page has actually changed. Okay, so very simple exercise, but it's just so that you can realize that you can actually get inside the container where we have a completely different file system, potentially, and you can make changes and spin up processes inside as needed. Now, how do we exit from here? Well, we can just type exit, and now we're back into our PowerShell prompt. Now, one thing that you should realize is that these changes that we made to the container are going to go away when the container is gone. So for instance, if I just do docker stop nginx test, right? So I'm going to stop that, clean this, and I'll do again docker run nginx test, and perhaps let's just use port 8080. Hit enter. Now we go back over here and let's use the correct port now. It's going to be 8080. We're going to see that we are going back into the original web page. So all of the changes that we made into our Nginx homepage are lost. So since most of the time we're going to be using ephemeral containers, we're going to be just destroying and creating new ones, how can we prevent losing changes like this, right? There should be a way to persist changes between container executions, and that is exactly what volumes are for. So let's switch back into slides for a moment so we can learn more about Docker volumes. Let's bring back our host machine, and let's say that we have a Docker container for our application already running in there. Inside our container, there is a file system structure, fully isolated from the host, and our application has chosen to store all of the user-generated files in the location represented by path2data here. Now here's something crucial to understand about Docker containers. They are designed to be ephemeral. When a container is removed or deleted, anything stored inside it disappears completely. So when we create a new container for the same application, all the data is gone. It starts only with the original file structure from its corresponding Docker image. Since containers are expected to be deleted and recreated frequently, how can we prevent losing data like this? This is where Docker volumes come into play. Let's see how they work. Once again, here's our host machine and our original container. A great feature of Docker is the ability to reserve space for persistent storage. This is a dedicated space on your host machine that Docker manages. Within this persistent storage area, we can create what is called a volume. Think of it as a special folder that Docker manages for us. Now, here's where the magic happens. When we start our container, we can tell Docker to connect our container's path2data directory to this volume. This creates a direct link. Whatever our application writes to that path actually gets stored in the volume. Even if our container gets deleted, our data remains safely stored in the volume. And here's the best part. When we create a new container, we can connect it to the same volume. Now our new container has access to all the data that was stored by the previous one. This is what makes Docker volumes so powerful. They allow our containers to be truly ephemeral while keeping our important data persistent and reusable. Let's see how to use Docker volumes in practice. Let's see how to use Docker volumes to prevent losing the data that is created during the container execution. So to start with, here we're back in the terminal, right? And let's go ahead and just stop this container. Okay, let's stop it. And let's go back to a clean screen here. So in order to use a volume, you're going to be using the following syntax. So let's go ahead and bring back our normal command line here. And what we're going to do is to add here the following. It's going to say -v for volume. And then what you want to do is to provide some sort of a virtual name for your volume. And if you wanted to, you could use an actual full path to represent the path in your host machine where you want this volume to live. But in this case, we're just going to be using what is known as a name volume. It is virtual, and the exact location is going to be determined by Docker. It's not really important. So let's name this volume nginx data with the colon, and then we have to specify what is going to be the location inside the container file structure that we want to link into our volume. So as we saw a moment ago, that location would be usr share nginx HTML. So that's the directory where we have this homepage for our nginx web server, right? And that's going to do it. So let's go ahead and hit enter, and our container has been created, right? So docker ps, here's our container. But more important than this, the volume has also been created. So if we now do, let's clean this, let's do docker volume list, we can see that we have our nginx volume right there. And we can see this not just in the CLI, but also in the Docker desktop GUI. If we go back here, if we go into volumes, we're going to see that the volume is right here. Okay, so this means that we now have persistent storage for our container. But how to use it? Well, let's do that same exercise that we did a moment ago. Let's change that homepage of nginx, and let's see if we can persist those changes across container executions. So let's go ahead and clean this, and let's do docker exec-it nginx test bin bash. So to open this bash session, let's hit enter, and let's switch to this location in the container that is linked into our volume, right? So let's go into usr share nginx html ls. That's our index.html page. So let's do the same thing as before. We're going to do echo, and then h1. We're going to say hello there again. Close this h1 tag, close double quotes, and let's pipe the output of that into, again, into the index.html page. Enter. Okay, so now if we go back into the browser, over here, we're going to refresh this page. And of course, we can see that our message is right there. Hello there again. Success. Now let's see if we can persist this across container executions. So let's go back into the terminal and let's exit this container. And not only that, let's go ahead and stop the container. So Docker stop nginx test, which, as we know, given the arguments that we provided, is going to not just stop, but kill the container completely, right? It's going to be completely removed. So if we now do Docker ps, there's nothing here. If we do Docker ps -- all, there's absolutely no container running here. But the volume should still be there, right? Docker volume list is right there. So let's clean this and let's rerun the exact same command, Docker run, with our nginx data volume right there. Okay, so let's run this and let's refresh our page. This is going to be a brand new container. We come back here, we refresh, and as you can see, the data is still there. Nothing has been lost because we have access to the data persisted in the volume. Okay, so volume is a key concept in Docker, and you're going to find that you're going to be using it a lot to persist the data that any of your containers is going to be storing. Okay, so hopefully that has been a good way to get used to all of these different Docker commands, and we understand much better how Docker images and Docker containers work alongside with volumes. So now it is time to look into how to create our own Docker image for our .NET application. So let's switch back to slides to learn more about that. .NET developers have two options to create Docker images. Use a Dockerfile or use the .NET SDK. Since most teams are using Dockerfiles today, let's explore that option first. We said before that a Docker image is a blueprint or template that contains everything needed to run your application. The traditional way to define this blueprint is via what is known as a Dockerfile. This is a simple text file where you specify all the instructions that are needed to prepare the Docker image. You place this file next to your application code and then execute the docker build command. That command talks to a Docker component called BuildKit, which is in charge of driving the build process. BuildKit creates the Docker image by reading one by one each of the instructions in your Docker file and generating layers or adding metadata to the image depending on the type of instruction. At the end of the build process, your new Docker image is ready to be used in your local dev box or can be published to a container registry anywhere in the cloud. Let's see how to build a Docker image via a Dockerfile in practice. What you can see here is the simplest possible .NET web application that you can create. And it is this application, the one that we're going to be turning into a Docker image and run as a container. Now, if you want to create this application, it is as simple as doing the following. So you can do .NET new, the type is going to be web, and the name that I gave this application is Hello Docker. Okay, so that's all I did. Now, if we see what's going on with this application, let's take a look at program CS. What you're going to find is that all it does is define an API endpoint on the very root of the web application, as you can see. And then when we do a GET request into this endpoint, it's going to just go ahead and return hello world as simple text. And to confirm this, what we can do is just run the application. Let's do .NET run. And in my case, the application is running, as you can see, in localhost 5048. So let me just copy that. Let me bring that into my browser. I'll paste that in navigation bar. And as you can see, all it does is return hello world. Super simple. Okay, so let's go back into VS Code. Let's collapse this, close that. Let's go back to the File Explorer. And one more detail about this is that this application has been built using .NET 8. As you can see, target framework is .NET 8 because it is the latest stable version available at the time that I'm recording this video. Okay, so the first step towards turning this application into a Docker image is to prepare it for containerization. And that means that we don't really want to bundle the source code of the application into our container. What we really want is to come up with some sort of output, the output binaries for the application that will be used to execute the application at runtime. And to do that, there's a very specific command in .NET that you can use to produce that output. So let's go ahead and open up our terminal once again. And the command that you want to execute is .NET publish. Now, what you want to do here is to provide the name of the project that you want to publish. In this case is hello docker.csproc. Let me collapse this for a bit. And then what you probably also want to do here is to specify what is going to be the output directory where you want to send these output binaries, right? So I'll say -o for output, and let's just name it publish. It could be any other directory. I'll just choose to name it published. So let's hit enter. And as you can see, it went ahead and created our output into this location, hello docker/published. And if we go ahead and open up our Explorer, we're going to see that that folder is right here. It's published. And if we explore a little bit of what's going on there, we're going to see that here we find, of course, our application DLL, right? Here's our DLL. We find our app settings.development and app settings.json file. And we also find a few other files that we're not going to take a look right now, but these are kind of the minimum necessary to run the application that we have created. Now, one thing that you should notice here is that this application was created in release mode. So if you collapse this, notice that the application is actually sent first into the bin/release directory, right? That means that it was created in release mode, which means that it has removed all of the debug symbols that you usually use for debugging the application locally, but you're not going to need when you deploy this application into production. So you want to make sure that you always publish your release application and not a debug application. Now, in the past, to do this, you would have to add a parameter -c and then release for release configuration. But in latest .NET versions, release is actually the default configuration when you do .NET Polish. So you don't have to specify release anymore. It will by default go into release. So that's the first thing. Now, the next thing, going back into the Explorer, is that we have one file here, that's an interesting file, hello docker.exe. Now, that file is known as the native executable wrapper, right? And the purpose of that file is that if you are, in this case on Windows, you can just go ahead and run the application by running that exe file over there. And of course, that file is going to eventually invoke the DLL that we have created. Now, in our case, since what we want to do is to create a Docker image and a Docker container, and we might want to make it portable, right? So we want to execute it for whichever platform we decide to create our Docker container. We don't really need to bundle that exe there, right? Because that means that we will always be creating this application to run on Windows, but it's not true. Even if I'm creating this application right now on Windows, we want to execute it in many possible platforms. Because of that, we're going to go ahead and remove that exe, right? Because it's just adding more files than needed into our Docker image. So let's clean this. And let me actually go ahead and first, let's just remove this publish directory. Let me delete that. Okay, it's gone. And then let's bring back our .NET publish command, but then let's append one more argument here. And it's going to say /p to add one more parameter. That's going to say use app host equals false. So when I hit enter now, it's going to run through the same process. But if we take a look at the publish directory, we're going to see that that executable wrapper is no longer here. Notice that it is no longer anywhere to be found. So that strips out that executable wrapper. And it is a common practice to do this when you're going to create a Docker image, because of course, like I said, you want to run the Docker image in as many environments as possible. You don't need to be constrained to that exe, like in this case for Windows. All right. And so with this done, we now have our publish directory. And notice that this doesn't include anything about the source code. It's just the output needed to run the application. And this is what we need to bring into our Docker image. Now, the traditional way to turn everything that we have in our publish directory and package it into a Docker image is by writing a Dockerfile. But before we write our Dockerfile, let's go ahead and enable a VS Code extension that is going to make the job a little bit easier. So let me go ahead and open up my command palette, and let's go into focus activity bars to show my activity bar on the left side. Let's open up these three dots. Let's go into extensions. And here, what you have to do is just look for Docker. So it should be the very first one over here on the left side. Collapse this. So this is a Docker extension, which is going to enable several new commands and features into VS Code, including the ability to present intelligence as you write your Dockerfile, which is what we are after here. So let's go ahead and just click on that install button so that extension gets installed. So let's close this and let's go back into our file explorer. I'm also going to go ahead and hide this activity bar for now because we're not going to be using it. All right. Now let's go ahead and expand this a little bit, collapse that. And what we're going to do is to create a brand new file that we're going to name Dockerfile directly at the root of our project. Okay, so I'm just going to go ahead and click on this plus button over here to create a new file, and it has to be named Dockerfile, exactly like that. Okay, and then we're going to collapse this for a moment so we can focus on this Dockerfile. Now, as we know by now, the way that you define your Docker image is by specifying all of the instructions that are needed to compose everything that we want to package into that image. And because of that, the first thing to do here is to define what is going to be the base image that is going to provide the core OS and perhaps the .NET runtime that we want to use for our application. But what image would that be? Well, for that, we could go straight into Docker Hub, but since there are multiple images related to .NET, one thing that you can do is actually start in the following page, this one here, and you can see the URL over there. This is inside Microsoft documentation. So this is the page that describes all of the .NET container images available and many details about those. And the thing that I want to show you here, if we expand this section here, so there's this link here that says Docker Hub repositories. And if you click in there, you're going to be taken into this section, which shows the main image repositories related to .NET applications. So for instance, you would use the SDK image if you need to build an .NET application inside your Docker image. And we're going to take a look at this one a bit later in this video. But if you're building a web application, as we are doing right now, the right image to use would be the ASP.NET image, as you can see right there. If you're not building a web application, but any other kind of .NET app that does not need the web requirements, you could use the runtime image over here. For instance, a background service, you could use that image for that. And there are a few other images, as you can see over here. Plus, there are also nightly image repositories. If you want to go into bleeding edge stuff, that's also available over here. Plus many other details. But like I said, what we want to do is to build an ASP.NET Core application. So we want to use the ASP.NET image. So let's click on ASP.NET. And this is going to take us now into Docker Hub, where we can see all of the details about the .NET image that has the ASP.NET Core runtime. So this is going to be an image that already has a base OS plus all of the ASP.NET Core requirements. Now, this ASP.NET Core image is generally going to be based on Linux and not on Windows, because Linux images are much smaller, are more efficient, are faster, and they are broadly supported by most container orchestrator systems like Kubernetes. And since .NET is cross-platform, you can easily use any image that is based on any Linux distribution. Now you can see the main tags that are available for this image over here, right? So it says 9.0 here for the one that supports .NET 9 and also 8.0 for the one that supports 8.0. But if you're curious and you'd like to know about all of the tags available for ASP.NET Core applications and which exact OS is behind those, what you can do is just scroll down a little bit. It's going to be a section here where it says full tag listing. You can click on this GitHub link over there. So click on that. That's going to take you into this page that is going to give you the full listing of all of the tags that are available for ASP.NET Core. For instance, we're going to be using actually tag 8.0 for application, because remember that we created an 8.0 app. So if we do a quick search here for 8.0, you're going to see here, let's scroll up a little bit. So we are in the Linux AMD 64 tag section, because there are multiple platforms also supported for our images. And in this section, we're going to see that 8.0 is actually right here. So it is tagged as 8.0, but also as 8.0.12, but also as 8.0 Bookworm Slim. And if you see on the left side, you're going to see that this is actually based on Debian, the Debian distribution of Linux, Debian 12, specifically the Bookworm release, as you can see right there. But just like that, as you can see, there are many other options, right? So you can see that we have Alpine, we have Ubuntu. There are several variants that you could choose from for specific versions, depending on what you want to do. If you're interested in Windows images, you can also look here for Windows. And you're going to see that down here, there are also versions that are based on the Windows OS. Now, most of the time, you're not going to be using a Windows image because it is, like I said, they're much bigger. They're not really efficient, and they are harder to get supported in container systems. So unless you need something very, very specific of Windows, the general case is that you're going to be using a Linux image, right? So let's go back into this page here, and let's go back into the top. Like I said, we are creating a .NET 8 application. So what we want to do is to grab everything here from the registry name, which is mcr.microsoft.com/.NET, which is a repository, and then 8.0, which is a specific tag that we want. So let's just copy that. And let's get back into VS Code. And in our Dockerfile, the first line that we're going to write is the one that specifies that we want to use that image as our base image. And for that, you use the from keyword, and then you're going to just paste the actual image. So let me do this. So we are pasting that image. Now, there are a few parts in this image name that you should understand. And it starts with this first part here that says mcr.microsoft.com. This is known as the container registry. So like I said, this is a special kind of online storage for Docker images. We saw the listing in Docker Hub, but the actual registry for Microsoft images is mcr.microsoft.com. That's the official place where you should be getting all of your Microsoft related images. Now, the next part here, this one that says .NET/ASP.NET, is known as the repository. So this is a dedicated, let's say, folder or a project space for storing a series of related container images. And then, of course, at the end, we have what we know as a tag, 8.0. Now, the next thing, if we keep going down, is to specify what is going to be our working directory. So this is the location that Docker is going to be using inside the image to do any file-related operations. So for that, let's just do work dir. And in this case, we're going to just say /app. So that means that any operations that we perform in the image from here on are going to be using the /app directory as the default directory for that file-related operation. Next, what we want to do is to specify what is going to be copied inside this image. So if you open up Ctrl+Shift+E, let's open up our file explorer. Remember that we placed everything we need inside this publish directory, right? So this directory right here. So we need all of that into the image. How do we get those files into the image? Well, by using the copy instruction. So you just have to type copy, and then the directory is named published. So published / and then on the right side, we're going to say that it has to go into the current directory. So we can do that with this. Current directory, remember, is going to be /app because we said work dir. So this line is just going to take everything from our host machine, right, into that /app directory. And then we only need one more instruction here to get this done, which is going to be the instruction that specifies what exactly needs to be executed inside this container to get our application started. So that is known as entry point. So entry point, and inside here, you will have to specify what is going to be the executable application to run inside the container. In our case, that's going to be the .NET application. And then we have to specify just one argument, which tells it what is the DLL that represents our app. Remember that DLL is on the left side here, is called hello docker.dll. So let's see if I can just copy the name here. I'm going to just copy that, and I'm going to paste it on the right side. Right? So that is really the kind of the minimal stuff that you're going to need to write your Docker file. Docker files can be really big and have tons and tons of other fun stuff in them, but this is the minimal. So you specify your base image, you specify what is going to be your work dir, then you specify what to copy into that image, and finally you specify what exactly to run from those files that you copied into the image. Right? So now we have that done. We are ready to go ahead and build our first Docker image. To build our Docker image, we're going to be using the Docker CLI. So let's go ahead and open up our terminal. So Control J on Windows. And perhaps let's go ahead and expand this terminal a little bit so we can see better. And the command that you want to use here is Docker build. So this is the command that can create an image based on your Docker file. Now you have to specify two arguments here. The first one is going to be -t, where T stands for tag. And this is the one that you want to use to give a name to your Docker image. So in this case, to keep it simple, let's just name it Hello Docker. Could be any other name. But just notice that even when the argument is tag, -t for tag, we're not really specifying a tag here, but just the name of the image. Okay. And then the next argument we're going to be using is what is known as the location of your build context. So the build context is really the set of files that you want to transfer into the Docker daemon. And usually what you want to do here is just to specify the location where you also have your Docker file. So if we go ahead and open up Ctrl+Shift+E, let's see our file explorer, we're going to see that our Docker file lives at the root of the Hello Docker repository, which is also the location where I have my terminal right now. And because of that, we can go ahead and just put a dot here, where dot specifies current directory, right? Now, because we already have our files to include into the Docker image in the push directory, this is a little bit overkill to send the entire repository into the build context. But later on, you're going to see how we're going to have a way to filter the files that are going to go into the build context so that we can produce our images in a more efficient way. And we're going to go into those later. But one more thing is that if your Docker file actually lives in a different subdirectory, you can use the -f argument to specify the location of the Docker file. But like I said, the convention is really to keep it at the root of your project repository. Now let's collapse this. And now let's go ahead and hit enter. So let's see what happens now. So now what's happening is that Docker is going one by one through all of the instructions in your Docker file, and it executes them to produce your image. Now, if you scroll up a little bit to see what actually happened, you're going to see that initially it will go ahead and just figure out a few things about what needs to be done. Like for instance, what is the Docker file, right, that needs to be used, what metadata needs to be read about the base image, and if we have a Docker ignore file, which we're going to cover later on. And it also transfers a little bit of information about what needs to be done into Docker daemon. But then the actual work starts over here, right, where the first step is going to be to, well, download that base image that we specified, right? And that's going to be all of these lines over here. These are all of the layers of that base ASP.NET Core image that needs to be used for our Docker image, right? So all of that happens. And then we're going to go ahead and, like I said, it transfers the build context, which in this case is just 27.69 kilobytes, right? So that is transferred into the Docker daemon. So our Docker is ready to work with our files. Then next instruction, like we said, we want to specify what is going to be our working directory /app, and then it copies from the build context, it copies everything from the push directory into that /app directory, right? And then it will go ahead and actually produce our image with all of the lines that you can see over here, which end up in naming our image as Hello Docker latest. It also appends docker.io at the start because it assumes that the image might go into Docker Hub, but the image name is Hello Docker with the latest tag. By default, every image just gets latest, only if you specify a tag. So if this is true, what we can do now is clean this and say Docker images. And sure enough, we can now see that our new Hello Docker image is right here. Okay, we can see that it uses the latest tag. Here's the image ID, here when it was created, and we can even see the size of the image. Now, one thing that you can actually explore a little bit more here, if you're curious, is, well, what are all these layers that actually went into this image? And what you can do is just inspect briefly what's going on there by going into Docker Desktop. So let me show you. Let's go into Docker Desktop. And if we go now into images, we should be able to see our brand new image over here at the bottom. And what you can do is just click on the Hello Docker image. Let's see if we can expand this a bit. And what you can see here in this section is all of the layers that now compose our brand new image, right? So for instance, if we click on this very first layer over here and we click on the command, you can see the actual commands that were used to create our base image. In this case, it's just a bash script that we can assume that what it's doing is preparing all of the files of the base OS. Like I said, by default, we're going to be using Linux images, and this is going to be a Debian image. So that's what it's doing, is preparing that distribution for our base image. And then we'll go ahead and start customizing it for ASP.NET Core applications. So for instance, layer 1 is going to set a few environment variables, including this important one, ASP.NET Core HTTP ports 8080, which defines that by default, our application in a container is going to be listening on port 8080, right? Then we keep going, and it's going to run a few commands to install a few utilities that may be needed by our image. Then we keep going, and this is dealing with the Linux user that's going to be specified for our image. Then we have a new environment variable over there. Then we keep going, and then it is copying a bunch of files related to .NET into our image, followed by this other line here. We are specifying the version of ASP.NET that we are going to be using in this case. Then we copy even more files that in this case are related to ASP.NET Core. And then finally, at layer 9 is where we go ahead and run our own set of instructions to set the work dir /app, copy the files from publish dir into the image, and finally we specify what is going to be that command to kick off the execution of the container with our hello docker DLL. So anytime you're curious about, well, what layers are present in the image that you're creating, you can always come here into Docker Desktop and explore your image layers like that. Okay, so going back into VS Code, we have our image ready, and we are ready to run this image to turn it into a container. Now, to run our Docker image, all we have to do is choose the Docker run command. So let me clean this for a moment. And before executing Docker run, what I like to do is to actually stop our previous Nginx container, which I think is still running, to make sure that we avoid any sort of port conflict. So if you do Docker PS, we're going to see that we're still running Nginx, right? Which happens to be mapped into the exact port that we are going to be using now, 8080. So let's make sure that we actually Docker stop our Nginx test container. Okay, now it is stopped, and now we're ready to run our image. So like I said, what you want to do is do Docker run, and then the name of your image, which in this case is hello Docker. Since it has the tag of latest, we don't even have to specify the tag. That should be good enough. But one thing that I really like to do is to specify the --rm argument here, which, as we know, is going to be used to remove the container once we stopped it. Okay, so now let's go ahead and hit enter. And as you can see, this is a familiar output for any ASP.NET Core application, which is telling us right away that the application is running and it's listening in port 8080, right? So you should be able to reach out into our application now in the Docker container at that port. So if we go back into our browser, where we're looking at the ASP.NET Core Docker Hub page, let's just use this to try to go now into localhost 8080, which is where we were running Nginx before, as you remember. So let's hit enter, see what happens. Of course, we cannot reach a container, and probably you know why by now. It is because, well, we have not done the appropriate port mapping, right? So we can fix that very quickly by going back here. Let's stop this process, and then let's clean this, and let's run our command once again, but now specifying that we want to map some port into port 8080 in the container. To keep things simple, let's just map once again 8080 into port 8080 in the container. Remember that left side is your port in the host network of your local host machine, and the right side is the port that the container is listening into. So this time, let's go ahead and run this, and let's go back to the browser. Let's refresh this, and as you can see, it is now coming back with the appropriate hello world message. So our application is now running inside a Docker container. Now let's go back into VS Code, and let's just stop this. And one thing that may be bothering you right now is that, well, if we ever want to create a new version of our application with a new corresponding image, we'll have to go through this process of first publishing the files over here, right, in the publish directory, and then running the corresponding Docker build command, right? But fortunately, there is a more efficient way to do this that doesn't involve all of those steps. So next, we're going to be taking a look at what we know as multi-stage build. A multi-stage build is really a Docker build where we're going to have potentially multiple stages of work across that build process. And that means that if let me just collapse this for a moment and let's get back into our Dockerfile here. That means that before executing these lines here that actually create our image, we can have a preliminary stage where Docker itself is going to take care of building our application and generating that publish directory, right? So that the next stage can take those files and produce the final image. So I want to show you how that works. But before doing that, what we should do is to also introduce what is known as a Docker ignore file, because we don't want to keep sending all of the files in our project into the build context, right? Because that's just using too much space and it's also consuming time as we try to build our images. So let's do this. Let's go over here. And at the very root of our project here, let's click here to create a new file. And that file has to be named .dockerignore. Okay, this is going to be very similar to a git ignore file, if you're familiar with that, where you specify which files should not get into the build context. Now, to save some time, I have prepared a small list here of the files that I like to exclude, files and directories. So let me just copy this from my cheat sheet for a moment, right there. And let's go through this very quickly, right? So we don't need to include either the bin or obj directories into the build context, because like I said, Docker is going to take care of building and publishing the files itself. So we don't have to provide it any of already compiled binaries or temporary obj files. Also, the stuff that we have under properties is really designed for local development. It has nothing to do with an image that's going to be running in production. So we don't need the properties directory. We also don't need to include the Docker file itself, right? Because that's going to be used to drive the build process, but we don't have to include it as part of the build context. We also don't need to include the Docker ignore file itself. We don't need to include development.json because, like I said, this is not for development. This is a deployment to production. So we don't need anything that's going on there. And we also don't need the solution file. That's just not going to be used. Now, we could also include in this file our publish directory because we don't want to copy that into the Docker image, but we might as well just delete it because this was a temporary exercise and we're not going to be publishing our application for the image anymore this way. So let me just right click this and let's delete this. And well, with all of these exclusions, really what should be transferred into that build context should be only our abstract.json file over here, our project file, and our program.cs file, right? That's really all we need to compile our application. Okay, so now let's go ahead and close this file and let's focus on the Dockerfile. Like I said, with a multi-stage build, we can have several stages of work across this build process. So what we're going to do is perhaps I'm going to collapse a few of these lines. And now at the very top, we're going to use a new from statement to specify what is going to be the image that we want to use to build our application. So I'm going to copy this for a moment over here. But the thing is that we cannot use this ASP.NET image right now because that one only includes the runtime. So that is the files needed to run your application in production. But that doesn't include any of the .NET SDK files that are needed to compile the application. Because of that, we have to change this into .NET SDK, like that. And of course, we need to specify the right version of the SDK that we want to use. Okay, so this is going to be our first stage, and we're going to actually name it as build. Okay, so this way you're specifying that this is a first stage. It's going to be our build stage, only use it to compile the application. And the output of this stage is going to go into the next stage where we actually build the image that's going to run in production. Now, just like we did with our final image, we're going to use the work dir instruction here to specify what is going to be our working directory inside that image. So let's just name it src. And then we can go ahead and use the copy instructions to copy really everything from our build context into our temporal build stage in the image, right? So it's just dot and then another dot. And finally, we want to run the command that is going to take care of producing our publish directory inside this first stage of the build process. So remember that command is .NET publish, but to execute that command inside our Docker build process, you want to use the run instruction, right? So run you can use to execute a command. And that command is going to be, as you may remember, .NET publish. Then you want to specify what is going to be the name of your project. So that's going to be hello docker.csproc. And then we're going to send an output. So let's do this. Yes, -o published. And then let's also remember to do /p use app host equals false. Remember that we don't need to include that wrapper that produces the exe because we want our image to be as portable as possible, right? So with that, this first stage is complete, and the end result is going to be that inside this first stage, there will be a publish directory that has everything we need to prepare our image for execution. Now we go ahead and continue with the second stage, with the start in line 6 here, the same thing that we had before. But the difference is going to be that in this copy instruction, we're no longer going to be copying from the publish directory in our local host in our project. We need to copy the output of the first stage. So to do that, we're going to change these lines into copy. We're going to say from equals, and then the stage, as remember at the very top, it says the stage is built. So let's copy that and we paste that here. And then from that stage, well, what is going to be the actual directory to copy? Well, as we know, that directory is /published. So we copy from /publish into whatever is our current directory. So it's going to be a dot, and that dot in this case represents /app, just like before. And then the rest stays the same. So now we have an improved Dockerfile that is able to build and produce a publish directory by itself using the .NET SDK image first, and then it uses the SVNet core runtime image to create the final image that we're going to be running in production. Notice that because of this, our image is not going to be as big as it could be if we just use the SDK image for the entire process, right? We don't want to include SDK files into our final image because it's going to make it bigger, right? We only need the SVNet core image, which is linear and specifically designed to run your application in production, right? So with that done, let's see how this goes. So let's open up our terminal here. Let's expand this perhaps. And if we do Docker images, we're going to remember that we do have our hello Docker image right there. So what we're going to do is just remove that image now. So Docker RMI is the command to remove an image. Hello Docker. Okay, so the image should be gone now. Yeah, it is gone. And now we're ready to rebuild the image. So let's do Docker build, like we said, -t, hello Docker, and then dot for the build context. So let's hit enter. And the process is going to be similar, but this time, as you know, we need to go through 2 stages to complete our image. So if we go a little bit up, we're going to see that now we have this step here where we use the .NET SDK, right? We download the .NET SDK to do the build process. Then we also have in the second stage, we are downloading the SVNet core image layers. And then we go ahead and do the steps in the first stage to publish our application. And later we use that output here to produce the files that are going to go into our final image. Now the result is the same thing, right? So if we do Docker images, we're going to see that our hello Docker image is right here. The result is the same, but notice that this time we did not have to produce that publish directory anymore, right? We don't have to do this anymore. We just make changes into the application, and then we produce a brand new image with this improved Dockerfile. Now, just to confirm that everything is working as expected, we can go ahead and run the application just like we did before. Okay, it is running, same output, going back to the browser. If you just refresh this, we're going to see that it's the same result, right? So hello world. So let's see what will be the process for us to come up with a brand new version of our application and generate a brand new image. Because now we have the build process ready, so it should be pretty straightforward. So let's go back into our VS Code instance here. So let's do Ctrl+C to stop the application, which also removes that container. And let's close this for a moment. And let's Ctrl+Shift+E, let's collapse Dockerfile, and perhaps let's go into Program CS, and really all we're going to do is to make a small change on the message that we have here, right? So perhaps instead of hello world, let's just say hello Docker. So we have created, or we have made a change into the application, and now we want to produce a brand new image. What do? Well, we just go ahead and go back into our terminal over here. We're going to clean this. And the first thing that we should do here is to actually provide a correct tag for the image that we already created. So if we do Docker images, remember that currently we are using latest tag for our image, but that's not really a good practice, because if you keep using latest, you start losing track of your previous images. Latest is going to be always associated to the very last image you produce, but then you cannot go back to other ones. So in order to properly tag your existing images, you can just use the docker tag command. So we're going to say, let's clean this, docker tag, and we're going to say that the current image that is just called hello docker, you can say also hello docker latest if you want, we want to retag it as hello docker 1.0. You can use any version scheme that suits your needs over here. I'm just going to go with 1.0 because it's just simple and easy to understand. And then we hit enter. And after that, we do Docker images. And you're going to see that we have our brand new image tag over here with 1.0. Now, of course, you can notice that the image ID is the same in both cases, because as I said before, the tagging system is just a way for you to create pointers to specific points in the lifetime of your images, right? But that doesn't change the fact that it is essentially the same image. So latest and 1.0 are really the same image. It just happens to be that we have two ways to refer to that image. And that's okay. But because of this, now we have a way to introduce a brand new version of our image that includes our changes. So this time, let's clean this, and we're going to do Docker build. Remember that this is how we did it the first time, but this time we can actually provide a tag as part of the build process. So we can say column, and this is going to be version 1.1. Okay, so the image has to be produced with our changes and then with a brand new tag. So let's hit enter. And there's going to be a bunch of caching in there because not a lot changed really. But now, after this is complete, if we clean this and do Docker images once again, we're going to see that we now have our version 1.1 of the image over here with a brand new image ID that has nothing to do with version 1.0. And if we now run the application, so let's do Docker run, and it's going to be a similar command, but of course, we now have to specify the brand new tag. So it's going to be 1.1, hello Docker 1.1. So let's run it, enter. Application starts, and if we go back into the browser and we refresh this, we can see that the message has changed because we have introduced the very first change into our application. This is our hello Docker version 1.1. Okay, now let's go back into VS Code and perhaps let's just stop our application. Let's close this and let's get back into our Dockerfile. So before we go into the next topic, where we're going to talk about a different way of building your Docker images, one thing that you should realize is that there are ways to make your images significantly smaller by picking the right base OS. And the thing is that when you think about containers, those containers should be as small and as lightweight as possible so you can easily spin up and tear down those containers all the time, right? So if you take a quick look at this page over here, which we took a look at earlier, this is the page that talks about Docker containers for .NET, and here's the URL if you want to take a look. There's a section that talks about images optimized for size. Here you're going to see that there are distributions like Alpine, Mariner, Distroless, and Ubuntu Chiseled that are way smaller because they don't include perhaps as many utilities as you may find in an image like Debian, right? And they also have a smaller attack surface, right? So they are more secure than what you would find in another image. So let me show you what you could do to use one of these other base images, and let's see if our application behaves the same or behaves in a different way. Now we go back into this other page that we looked at before. Here's where we eventually found our base image for our application, right? So we said that we could do 8.0, and that's how we found that the image that we wanted to use would be this one here, right? The base image, which is based on Debian, right? However, we can also use this list here to filter for Alpine, right? So let's go for Alpine Linux. And again, we're going to see that there are several versions available. But for instance, we could go with this one here, right? Which is based on Alpine, and that actually has the simple 8.0 Alpine tag. So by using this, we can switch into a different OS that is going to be much smaller. So let's go ahead and grab this 8.0 Alpine tag. Let's copy that. And let's get back into our Docker file. And really all we have to do is change a little bit, right? So let's go into our first stage and switch from 8.0 into 8.0 Alpine. And same thing for our second stage, where we produce a runtime image. Let's switch it into 8.0 Alpine. And that's pretty much it. Now we can go back into our terminal. Let's open up our terminal. Let's clean this, perhaps expand once again. And let's do our Docker build process once again. So Docker build, this is going to be, well, version 1.2 of our image, right? Now optimize it for size. Let's hit enter. And a few layers are going to be cached, but some others will have to be downloaded again because now we're switching the base OS, right? And the resulting image should be much smaller. So it's going to take a few seconds and it should be, yep, it is done by now. So if we now clean this and do Docker images, we're going to see that our brand new version, which is right here, version 1.2, right, of our image, notice the difference in sizes, right? So notice that our previous version was 320 megabytes, but this version is now only 157 megabytes. Like I said, that is because this image may not include, for instance, bash, but what if you don't actually need bash in there? You can just do with a simpler shell that is included in the Alpine image. In the end, the behavior should be exactly the same. So if we clean this and we do Docker run, and let's switch to version 1.2 of our image, let's hit enter. The application is started normally, and if we go to the browser, we're going to see that the behavior is the same, right? It just keeps showing our hello Docker text over there. So this is just something to keep in mind as you try to make your images much smaller, so they're more lightweight and quicker to run and quicker to dispose. So with that done, let's go ahead and switch into slides. We're going to be learning about a more modern way to create Docker images by using the native .NET container tooling. .NET developers can create Docker images for their applications by using the .NET SDK. Every .NET application is defined in project files, and in this file you can define several essential details like the project type, target framework, and which files to include or produce as a final output. But it is also possible to specify multiple details about the base image that should be used to containerize the application, as well as info about the image to be produced, and even execution details for the corresponding container. The .NET publish command of the .NET SDK is able to gather all this information from the project file, plus command line arguments, to produce a Docker image for your application, always using the correct base image by default. And on top of that base image layer, it adds another layer that describes everything about your application, including files, dependencies, configurations, and how to run the app. So when comparing this way of creating images with the traditional Dockerfile-based approach, you'll get two key benefits. You don't need a Dockerfile, since the recipe to build your image comes directly from your project file and command line arguments, and you don't even need Docker in your box, at least not for just building the image, since the .NET SDK includes everything that's needed. But those benefits also come with a few challenges. There's limited customization to define your images. Most of the things you can do in a Dockerfile you can do with the .NET SDK, but not all Dockerfile instructions are supported, including the run command. Also, the .NET SDK always generates a single layer for your application, regardless of what changes you made, making the caching experience poor in comparison with the rich caching offered by Dockerfiles. Let's now see how to generate Docker images with the .NET SDK in practice. Let's see how to create a container image in a more streamlined way, not using Dockerfiles, but instead using just the .NET SDK. And to start, we're going to go ahead and just get rid of these two files, our docker ignore and our Dockerfile, because they're not going to be used anymore. So let's just right click on those, click delete. Okay, they're gone. And the way to do this is going to be via the .NET publish command that is part of the .NET CLI. So let's open up our terminal, Ctrl J here. Perhaps I'm going to collapse this and expand this a little bit. And the command that you want to use is similar to what we have done before, right? So .NET publish, but this time we're going to specify the following arguments. First, we're going to specify what is going to be the target OS. Since we're producing Docker images for Linux, we have to say here --OS Linux. The next argument is going to be the architecture, because even if it is for Linux, it could be one of many architectures, right? But in this case, let's go ahead and use for architecture is going to be x64. Now, this architecture argument is kind of optional because if you don't specify it, it's going to just default to x64. But it can't hurt to be very explicit on what we're trying to produce here. I think lastly, you want to specify the following argument, which is /t, which stands for target, and then publish container. A target is a concept of the MS Build engine, which is what we use to build our .NET applications, but we're not going to go into those details. So just know that this target is required to instruct the .NET Publish tool that we do want to create a container. Okay, and with that, let's go ahead and hit enter. And as you can see, this time .NET Publish produced artifacts that are specific for Linux, and you can see that over here, right? So it went for a Linux x64 output over there, and then a publish directory, but also it went ahead and produced an image. I mean, it didn't just publish, it did produce an image that it named Hello Docker. It put it on it the latest tag, and it used the .NET ASP.NET 8.0 image as the base image. And this is very interesting because we don't have a Dockerfile anymore, right? So where did it get all this information about the name of the image and the base image and all these things, right? So the thing is that the .NET SDK is able to follow a series of conventions where it just takes information from your project file to decide how to create the image. So if you go back, Ctrl+Shift+E, we're going to see that our project is named Hello Docker. So it knows about this and it can infer that for the name of the image. And not only that, if we go into the CSproc, we're going to see that we are currently targeting .NET 8.0, and we're also using the Web SDK. Because we're using the Web SDK and targeting 8.0, it is able to infer that we do want to use the ASP.NET, .NET ASP.NET 8.0 base image. Right? So this is why it is much easier to produce your Docker images by using this .NET Publish method as opposed to use a Dockerfile where you have to be very, very explicit. Now, if we collapse this, and perhaps expand this a little bit, and let's do Docker images. And this time we're going to see that our latest image has been overridden by the image that we just created. And this is the reason why we should always specify a concrete tag for every created image so that we don't keep losing track of images created before, right? So let's see how to specify a tag for our image while using the .NET SDK. But before doing that, let's make a small change in the application just so that later we can confirm that that change is present in the brand new image that we're going to be creating. So let's go ahead and open up our Explorer view, Ctrl+Shift+E, let me collapse this, and let's go into program.cs. As you remember, here all we're doing right now is just say hello Docker, right? When somebody invokes the get endpoint here. And what we can do is just perhaps improve this message a little bit so that, how about we make it show the OS and platform or architecture that is behind the image that is running this application. That is actually very straightforward to do with .NET by doing a little bit of string interpolation here. So we're going to do this. Hello from, and here we're going to do runtime information dot OS description, and we're going to say runtime information dot OS architecture, right? So this simple message should tell us, well, in what OS and in what architecture we are running when we invoke the API. Right, so with that in place, let's just close this, and then let's open up our terminal once again. Let's clean this. We're going to go ahead and do .NET Publish, so similar command as before, but this time we're going to append one more argument, which is going to be -b, and here we can say container image tag equals, and then we have to specify the actual tag, right? So in this case, it's going to be 1.3, and let's hit enter. Okay, so notice that this time it was able to actually use that new tag for our Docker image, And if we do Docker images again, we're going to find our brand new image over here. Okay, which is awesome. Now, one thing that may be interesting at this point is to inspect what happened with the layers in this new way of creating Docker images, right? So if we go back into Docker Desktop for a moment, and we go into images, we're going to see that we have our Hello Docker image right here, the brand new we created. So let's click on this and let's collapse this. What we're going to notice is that we mostly have the same layers as before, right? So it starts in this case from Debian, and then we start seeing a bunch of commands that are specific to ASP.NET Core. But the difference is really at the very end in this layer number 9. If you click on that, you're going to see that all it says is .NET SDK container tooling, some version, and that's it, right? So this means that we are not creating multiple layers for our application. So we don't have, because we don't have instructions, right? Like work dir or copy or entry point, none of those are available here. There's just going to be one more layer. So this layer 9 here in this case, one layer that has everything related to producing the image that we need for our app. So that's just something to keep in mind, because you're not going to enjoy some of the layer caching capabilities that we enjoy when using a Dockerfile. In this case, it's just one more layer for everything related to your application. All right? So now let's go back into VS Code and let's go ahead and run our new container and see how it behaves compared to the previous one. So Docker run, we're going to do --rm, so it's removed after we stop it. Let's not forget the port, right? 8080 mapped into port 8080 inside the container. Our image name, hello Docker, and then our brand new tag 1.3. Let's run this, and it runs just as before. And just as before, it is exposed on port 8080, which should work just as is in our browser. So let's go back to the browser over here, where before it just said hello Docker. So now let's go ahead and refresh this and let's see what we get. Yep. So as you can see, it is clearly telling us that now it is running from Debian, the Debian Linux 12, the bookworm release, and it is running on x64 because of the changes that we made into the application. So yeah, this is working as expected. Now, what if you want to be more specific about the Linux distribution that you want to use as your base OS and not just go for the default Debian distribution that we're using right now? So that is something that you can also do with the .NET SDK tooling for containers. Let me show you how to do that. So let's go back into VS Code over here, and I'm going to do Ctrl+C to stop my container. And let me collapse my terminal for now. Let's do Ctrl+Shift+E and let's go back to the project. So one way that you can do this, there are a few ways, but one way you can do this is by specifying more properties in your project file. So just like we have all of these properties here, you can start adding properties that are specifically designed to configure your container image or even how to execute your container, depending on your needs. For instance, here I could say container base image, right? And I'm going to close that here. And then right here, I can introduce whichever image I actually want to use as my base image. And just to not have to type too much, I'm going to just paste this small snippet here, which will be the image that we were using earlier with the Dockerfile, right? So mcrmicrosoft.com, .NET, ASP.NET, 80 Alpine. So that will be one way to say, hey, I do want to use this very specific base image for the image that you're going to go ahead and create. So that's one way to do it. But there's even, I think, a better way, by using more of the inference that comes with the .NET SDK. So let me show you this. Let's remove that. And what we're going to do is collapse this for a moment, and let's go back into our terminal. And let's bring back that .NET publish command that we had before. So .NET publish, there it is. And what you can actually do here is to switch from the Linux OS to an OS that supports Mussel. So you can say -Mussel. And by doing this, what you're saying is that you want to generate an image for an OS that uses Mussel as its C standard library. Now, Mussel is a lightweight, fast, and simple alternative to the GNU-C library or glibc used by most Linux distributions. And it happens to be that Alpine Linux is the most common Mussel-based distribution. So because of that, the tooling, the .NET tooling, is going to assume that because you specify Linux Mussel, what you really want is an Alpine-based container image. Now, just like I mentioned before, keep in mind that by switching to Mussel and by switching to Alpine, even if it's going to be smaller, that OS is not going to support everything that an OS based on glibc is going to support, right? So you're going to miss things, but if you're looking for a very small image, this is going to be the way to go. Now, let's go ahead and also switch the tag, right? It's going to be our tag 1.4. And now let's go ahead and run this. Let's see what happens. And as you can see, the publishing step now is targeting, or it went for a Linux Mussel x64 directory over there. And it targeted, as you can see here, the .NET ASP.NET 8.0 Alpine base image in a similar way to what happened when we did things with the Dockerfile. Right? And so, well, now let's go ahead and run this image and see, let's see if that works. So let's do .NET run, actually Docker run, hello Docker 1.4, right? Let's run this. So it is running as expected. And now let's go back to the browser. Let's see what we can find here. Let's go ahead and refresh this. And as you can see, now we are running on Alpine Linux, right? Again, on x64. So as you can see, there are many things that you can also do with the .NET SDK, just as well as what you did with the Dockerfile, but in a more streamlined way. And keep in mind also that you could also go ahead and, if I clean this, you could also go ahead and change your architecture, right? So it doesn't have to be x64. You could also change this to be an ARM-based OS if that's what you need. And in fact, if you want to know about all of these options available for you, what you can do is look at this page over here. So here is the URL, as you can see at the top, right there. And this is the page that gives you all of the reference for how to containerize your .NET app using the .NET SDK. So this is going to have tons of details of the many things that you can configure across your images, right, when you're using the .NET SDK. So take a look at this if you want to know more about what we can do. But for now, I think we are done in terms of how to build and run an image container locally. And what we want to do now is to switch into the next step, which is going to be how to publish this image into a container registry so that we can potentially run the image somewhere else outside of our box. So let's go back to slides to learn more about publishing container images. At this point, we have learned how to define our application requirements either via a Dockerfile or a .NET project file. We can then use either Docker or the .NET SDK to produce our container image. But clearly, there's no point on doing this unless we can somehow share our image. And that's where we can use a container registry, which, as we mentioned before, is a repository for Docker images, similar to how GitHub stores your code. You can publish your image to the container registry, and from there, it can be downloaded into any other DevOps or even to an orchestrator service like Kubernetes, which could run on-prem or in the cloud. There are two types of container registries, depending on the typical type of access you intend to provide to your images. Public registries allow you to make your images available to anyone, no credentials required. And the most popular one is Docker Hub, where today you can find thousands of images for every infrastructure service you can think of. On the other hand, there are private registries, where you have full control on who can access your images. Most cloud providers like Azure, Google Cloud, and AWS offer these kind of container registries, and this is where you'll usually publish your organization's container images. Just keep in mind that there are also ways to make your Docker Hub images private or cloud provider-based images public, even when that's not the most common use case. Let's see now how to publish your Docker image to a public container registry like Docker Hub in practice. Let's see how to publish our image into Docker Hub. Now, there are a couple of ways to do this. Just like we did with the steps for building an image, which we did it both via a Dockerfile and via the .NET SDK, you can also publish your image either using the Docker CLI or using the .NET CLI. So let me show you first the way to do it via Docker. The first step that you should follow as you're trying to publish your image to Docker Hub is to make sure that you have an account with Docker Hub, right? Because now you're going to have your own set of repositories for images in Docker Hub, and that needs to be tracked with your account. So to create an account here, if you don't have one, you can always just come here and click on the sign up button on the top right, click on sign up, and this is going to take you to the process of creating an account with Docker Hub, which is all free. Now, I already have an account, so I'm going to just go back to the home page, and I'm going to click on the sign in button over there. Sign in, going to log in here. Okay, and while being here, what I'm going to do is just click on the repositories link at the top over there. So click on repositories, and this is going to show you all of the repositories that you have already created. Now, I don't have anything right now. As you can see, it's all empty, but we are pretty much ready to publish our image over here. Now, images are published into these container image repositories, and I could go ahead and create a repository here first if I wanted to. However, the repository can also be auto-created for you as you publish it from the Docker CLI. So we're actually going to go ahead and do that. So let's get back into VS Code over here. And perhaps let's get more space here. The first step to publish your image is going to be to sign in your terminal with Docker Hub, right? So that it knows who you are and it gives you access to publish to your repository in Docker Hub. So first thing to do here is just to do Docker login. Okay, so this is going to kick off the login process. And as you can see, there is a web-based login option here. So what I'm going to do is just copy this code over here, to copy that. And it's asking me to go into this page. I'm going to click on that, open. Here we are. I'm going to paste my code over here, continue, and then I'll click confirm. Okay, and I should be all set now. I'm going to close this and go back to VS Code, where, as you can see, login has succeeded, right? So now the CLI knows how to talk to Docker Hub with our credentials. And now we need to decide what is going to be the image that we want to publish, right? So let's go ahead and clean this and let's do Docker images to see again what we have. The image that we want to publish is going to be this one over here, the very latest one, right? But it could be any other image that we have here. Now, before you can publish an image into Docker Hub, you first have to tell it what is the repository where the image has to be located. And the way to do this is by retagging your image with the correct repository as a prefix, right? Because the way it is right now, it really doesn't know. Everything is just living in your local machine. So a simple retag is going to let us accomplish this. So in order to retag our Hello Docker 1.4 image, we're going to do the following. We're going to say Docker tag Hello Docker 1.4. Okay, so that's the source image. And then the target one is going to be Julio C, because Julio C is my name in Docker Hub. So look at this. My repository is Julio C, right? So you have to use your one. And then we can name it again Hello Docker. It could be anything else, doesn't matter. And let's keep the same 1.4 tag. Okay, hit enter. And now if we do Docker images, we're going to see that we have our brand new image over here. Same thing as before, right? You can see that it is actually the same ID, but now it has the correct tag to publish to Docker Hub. And with that done, all we have to do is just say Docker push, that this is the command to publish images, and then we publish into the brand new tagged image. So Hello Docker 1.4, hit enter. And what this is going to do is to upload all of the layers that belong to our image, this time into Docker Hub, right? Remember that every image is composed of a bunch of layers, some of them for the base image, some of them from us. So what this is going to do is just publish all the layers over there. And at the end, we're going to notice if we go back into Docker Hub, if we refresh this page, we're going to find that our image now lives over there, right? Here is our image now live in Docker Hub. And perhaps we can click on it and we can see more details about the image, right? So you can see here's the tag, you can see the OS, and well, you could see more details about your image here, even how it was pushed, right? So there it is, and a few other details. Now, if you wanted to make it private, I think there's an option in settings here. Let me see settings. There is a way to make it private over here. There are limits on how many images or how many repositories can be made private in Docker Hub, but it's something that you could do if you wanted to. All right, now let's go back to repositories. And what we're going to do now is to go through a similar process, but this time we're going to use the .NET CLI. So to use the .NET CLI for this, let's go back into VS Code now, and let's collapse our terminal and let's open up our project file csproc. Remember that, like I mentioned, there are ways to add properties here to define details about your container image. And one of those details is the repository where you want to publish your image. So here what we can do is the following. We're going to add here container repository, right? We have to also close this. And what is going to be the repository? Well, we know that by now, right? So it is just, in my case, Julio C /hello Docker. Okay. So, and as with all of these properties, you can either set them in your project file or you can set them in your command line, right? So it's really up to you. Now that's that. And with that in place, we can go ahead and go to the command line and kick off the publishing process. Now, just so that you can see the complete experience, let me actually go back to the terminal right now. I'm going to do Docker logout, right? So this is going to be the way for you to log out of your sign-in session with, in this case, Docker Hub, just so we can see what happens if we try to do this without first logging in. Now, let's clean this. And let's do now our .NET publish command. So this is what we had before, but one more thing that we have to tell this command line here is what is the container registry where we want to publish the image. Because we have said, I mean, if we go back into the project file, let's collapse this for a moment, we told it what is going to be the repository, right? Which is Julio C hello Docker, but it still doesn't know where is the registry. It could be anywhere, right? So back in the terminal, we have to specify what is going to be that registry. So what I'm going to do is perhaps add it just after the architecture. I'm going to say the following. I'm going to say -p container registry equals, and in the case of Docker Hub, what you want to use is docker.io. That's the right way to specify that this has to go into Docker Hub. If you wanted to use something like Azure Container Registry or something in AWS or Google Cloud, you will have to change the value for this. Finally, let's switch our tag. We want to make sure we use a different tag for this. It's going to be 1.5. And we should be good to go. So now let's go ahead and hit enter. And what we're going to see, of course, is that it fails to publish the image because of this error here, right? So we don't have the credentials to push into Docker Hub. And that's because we logged out. Remember that we logged out from the command line. So that should help you realize that you have to be logged in first. Even if you want to publish with the .NET CLI into Docker Hub, you first have to log in. Now, just, I mean, we could do the login here in terminal, but I want to show you that you can also do this from the Docker Desktop UI, right? So over here, what you can do is just use this sign in button at the top, sign in. You can click there. And once again, this is going to take us to this page here where it is going to try to reuse the credentials that you have in the browser to log you in. So as you can see, it is pretty much logged in already. And I'm going to click on open, and that takes me back into Docker Desktop. And now, as you can see, I am signed in right there. So this signs me in here and also got me signed in the terminal. Going back here, we should be good to go this time. So let's clean this and let's run that same command, hit enter. And as you can see, what's going to happen once again is that all of those layers need to get uploaded into Docker Hub. And in the end, the image should get pushed as the message says over there. Very similar process. And so let's go back into Docker Hub. Let's close this tab and let's refresh this. Now, the repository is the same, right? So it is Julio C hello Docker. But if we go into the repository, we're going to see that our brand new tag is over here, right there, right? Pushed just a few seconds ago. And we can go over there and start looking at any details about this image. Notice that you can even see the layers. You can see all of the layers related to our image. But in the end, it's the same idea as before, right? So we now have a second tag for our image ready to go. And the next step is going to be, well, to actually pull down this image somewhere so that we can confirm that we can actually run the image outside of our deadbox. Now, at this point, we could certainly go ahead and find another computer, a PC or laptop, or a VM or a cloud service to go ahead and pull down this image and confirm that it can actually work beyond our deadbox. However, there is a much quicker, easier way if you just want to do a very quick check with this image that doesn't involve any of that. Let me show you how that works. So let's go into this same browser tab and let's go just into docker.com/play with Docker. So this is a page that, as you can see, offers hands-on Docker tutorials for developers. But the one thing that I really like about this page is that down here, you're going to see that we have this lab environment that is going to allow us to very quickly spin up a little sandbox where we can play with our Docker image and turn it into a container very quickly without having to actually provision any sort of a computer. So let's click on the Get Started button over here. This is going to take us into this page, labs.playwithdocker.com. And down here, you're going to find this login button that is actually going to try to, I think, log you in with your credentials from Docker Hub. So if you just click on Docker here, click on Docker. So that's going to sign you in right away if you're logged in with Docker Hub. And then all we have to do is click on the Start button. So let's click on Start. And as you can see, this is going to spin up this kind of a virtual session or a virtual sandbox where, as you can see, we do have a limited amount of time to test whatever we want to test with Docker here, which should be plenty of time. And what you can do now is click on this link that says Add New Instance. And this is going to likely spin up a brand new VM, or perhaps it's even a container. We don't know. But in any case, it is an environment where we have Docker available, and we should be able to pull down any of the images available on Docker Hub, at least the ones that are public, like ours, right? So let's go ahead and try to run our image that we just published into Docker Hub in this environment. So let's do Docker run, and then let's open up our port. So it's going to be 8080. Okay, and then let's go for our repository. In my case, it's Julio Sim, and then hello Docker. Then if I'm not wrong, the version was 1.5. I think that's the latest version that we published over there, 1.5. And then let's go ahead and hit enter. Okay, so as expected, it is not able to find the image locally, right? So it just pulled it down, and it is now, as you can see, it is now running and listening on port 8080 as usual, right? So the application is already running. Notice that we did not have to install anything on this virtual environment. It just works. And it just works because in this environment, Docker is available. And anywhere Docker is available, you can go ahead and run your Docker image. The Docker image includes everything needed to run your application. Now, the one thing here is that, well, as you can see, the IP that we have over here, right? This is an IP that's not really a public IP. So what we need to do is to make sure that we open the port that we need to open to be able to actually access this instance from the browser. If we want to just quickly test that the GET request can work. So for that, what we can do is use this button here that says Open Port, right? So you can click on Open Port, and then let's say we want to open 8080, just like we did in the local box. So let's put open 8080. Okay. And then what I can see is that there's a pop-up blocked here. So let me see if we can allow all these pop-ups here. So let's click OK. Let's try that once again. So let's click on Open Port 8080. Let's click OK. Okay. And as you can see, it right away took us into our page. And as you can see, we are running our Alpine image now, no longer in our box, but in the cloud. And it's a bit strange URL in there, but regardless, it is running in the cloud. And again, we didn't have to install anything. We just had to take the image over there, run it as a container, and there you go. It is running in the cloud. Okay. It is not a secure URL. As you can see, it is not HTTPS, but still it was able to open our image. And one thing you can try here, if you wanted to, is go back to the playground. And since we're doing Docker, you can easily just spin up another instance, right? So click on another instance. And once again, we can go ahead and do Docker run, and then -p 8080, map to 8080, and then will you see hello Docker 1.5, right? So that's going to run it once again. And now we have a second instance of our application running in the cloud, right? So it's up and running now. It is listening on 8080, and we can go ahead and once again click on Open Port. We're going to say yes, open 8080, click OK. And now we have a second instance of our application running in the cloud. Right, the URLs are similar, but not exactly the same. But regardless, now we have two copies of our little web app running in the cloud with very, very little effort. So this is the power of Docker. And As you start using it for more and more of your applications, you start realizing how powerful it is to be able to very quickly spin up your application without having to do any sort of work to prepare the machine for execution, right? So with this done, what I'd like to do is to show you a little bit of how Docker plays a key role across the entire DevOps lifecycle. So let's switch the slides to talk about that. Let's go through a brief overview of the role that containers play in the big picture of the DevOps lifecycle. It starts with our software developer, who can now forget about installing all sorts of tools and services in his box for local development. Developers can now run most of these tools and services as Docker containers, which are freely available on Docker Hub. When the developer commits and pushes the latest changes to a remote Git repository like GitHub or Azure repos, a continuous integration pipeline can be automatically triggered in services like Azure DevOps or GitHub Actions. This automated pipeline can build the code and run not just unit tests, but comprehensive integration tests that can use the same containers used for local development, so that the app can be tested with real external dependencies that can be started clean and destroyed in seconds. When all tests pass, the CI service can build a container image for the application and push it to a container registry in any cloud provider, which gets everything ready for the deployment stage. Next, the CI service can trigger a continuous deployment pipeline, which requests the deployment of the just created image into a container orchestrator like Kubernetes or Azure Container Apps. The orchestrator pulls the container image from the registry and then runs it as a container, which now becomes the live production version of the application, ready to receive requests from customers all over the web. As you can see, containers are a fundamental piece that ties together the entire DevOps lifecycle, from the dev box to automated CI/CD pipelines and all the way to production deployments. This makes them an essential tool for any modern software development team. So now that you have seen how containers fit into the DevOps lifecycle, you might be wondering how to go from understanding these concepts to actually applying them in real-world cloud applications. That's exactly why I created the .NET Cloud Developer Bootcamp. It's designed to take you beyond the basics and guide you through building scalable cloud-native applications using .NET, Azure, containers, CI/CD pipelines, Entra ID, microservices, and more. Through the bootcamp, you'll gain hands-on experience with the tools and platforms that will take you from a C# developer to a highly skilled .NET Cloud developer. You can find all the details at netacademy.io/bootcamp. Thanks for watching, and I'll see you in the next one.